The world's tallest building sank 43 millimeters into the earth while it was still being built. Now, 43 millimeters of downward movement might not sound like a lot, but the terrifying reality for the engineering team wasn't how far Burj Khalifa was sinking. It was how it might tear itself apart. This megastructure doesn't carry its unprecedented weight on one simple block of concrete. It relies on three massive structural wings spreading out over non-uniform ground. If the entire tower sinks perfectly evenly, it survives. But if just one of those colossal wings hits softer ground and begins to sink millimeters faster than the rest, the unequal pressure would snap millions of tons of rigid concrete and steel from the inside out. So, how do you prevent the heaviest building in history from destroying itself on uneven ground? Before examining the ground beneath Dubai, we must separate the popular fear of sinking from the engineering reality of settlement. Downward movement in a heavy structure is not automatically a sign of impending failure. Think of a heavy industrial platform or a massive cargo elevator. If that platform moves downward perfectly evenly, every object resting on it remains completely level and secure. This is known as total settlement. If every section of a building footprint moves downward by nearly the exact same amount, the structure remains entirely vertical. The elevation changes, but the structural alignment is preserved. The physical danger begins with a different mechanical process called differential settlement. This occurs when one side of a foundation moves further downward than another. When a foundation settles unequally, it stops acting like a level elevator and begins to tilt, forcing the stiff materials above to bend and deform. This unequal movement forces the building to rapidly redistribute massive gravitational forces across structural connections that were not designed to absorb extreme twisting loads. Now apply this severe structural threat to the unique geometry of Burj Khalifa. The tower relies on a specific Y-shaped footprint, pushing its load down through a central core and three distinct wings extending outward. Millions of tons of concrete and steel depend on that precise vertical alignment. If one of those sprawling wings were to settle even a few millimeters more than the central core or the opposing wings, the resulting stress would travel directly upward into the rigid superstructure. That internal stress could crack structural elements, damage elevator shafts, and severely compromise the stability of the entire tower. The real danger, hidden beneath the site, was never simply whether the tallest building on Earth would settle into the ground. The critical engineering challenge was whether each of its three sprawling wings would settle by the exact same amount. The challenge of keeping all three wings perfectly aligned would be difficult on solid uniform granite, but the site in Dubai is far more complex than a simple bed of loose desert sand. The ground beneath the tower consists of layered carbonate soils, calciciltite, and sedimentary rocks, whose properties shift and vary significantly by depth. Geotechnical investigations revealed that these subterranean layers do not compress with perfect uniformity across the entire footprint of the construction site. This geological reality immediately raised a series of severe practical questions for the design team. Could the outer edge of one wing encounter a stiffer layer of subterranean rock than the others? Could another section of the massive footprint deform slightly more under the concentrated pressure of the central core? Could a discrepancy of just a few millimeters below the surface drastically affect the vertical alignment hundreds of meters above the ground? In a super-tall structure, a tiny angular shift at the base translates into a massive horizontal displacement at the very top. Engineers knew that layered ground simply does not respond perfectly equally under an unevenly distributed load. The center of the Y-shape carries a massive concentration of weight, while the outer ends of the three wings distribute the load differently. If they merely placed the tower on a standard foundation, the varying stiffness of the soil layers would virtually guarantee differential settlement. The heavy central core would punch downward, while the outer wings might resist the movement, bending the entire structural frame. They could not assume that the rock beneath Wing A possessed the exact same compressibility as the rock beneath Wing C. To keep the three wings working together and to prevent catastrophic internal stresses, the engineers needed a solution far more sophisticated than a simple collection of deep pillars. They needed to force the foundation raft, the supporting piles, the surrounding geology, and the towering superstructure above to behave as a single coordinated system. The engineering solution to this uneven ground was a massive, highly coordinated underground system known as a piled raft foundation. This system begins with a highly reinforced concrete raft that is approximately 3.7 meters thick. This sprawling concrete pad acts as the primary interface, receiving the crushing gravitational load from the central core and the three wings, and spreading that pressure outward. But a raft alone cannot distribute the weight of the tower safely into layered carbonate rock. Beneath the raft, engineers installed a network of board-reinforced concrete piles, each approximately 1.5 meters in diameter and reaching 43 meters long. These deep piles are not simply standing on an infinitely strong, perfectly solid layer of impenetrable bedrock. Instead, they function through a complex physical interaction with the ground itself. As the weight of the tower pushes downward, resistance develops primarily along the rough vertical sides of the pile shafts through intense friction with the surrounding soil and rock. A limited amount of end-bearing resistance at the very bottom of the piles also contributes to holding the structure up. The critical engineering concept here is that the ground, the concrete piles, and the massive raft are designed to deform together under the load. The piles add extreme stiffness to the overall system and transfer the heaviest loads deeper into the more capable layers of rock. The foundation design was heavily governed by calculating acceptable limits for settlement and differential settlement, rather than simply asking if the ground could hold the total weight without an immediate bearing failure. Every component was calibrated to manage downward movement. Picture the gravity load traveling from the three towering wings, spreading across the massive 3.7-meter thick raft, traveling down the skin of the 43-meter-long piles, and dissipating into multiple underground geological layers. Yet, even this enormous underground system could not automatically guarantee that every wing would settle identically. The piled raft was an incredible achievement, but it needed help to maintain alignment. The next critical source of stiffness needed to lock the foundation in place came from a place most viewers would never expect. It came from the tower, rising above the ground. When engineers analyzed the performance of the massive foundation, one specific measurement became far more important than the total downward movement. Detailed engineering surveys recorded approximately 14 millimeters of maximum differential settlement across the measured profile of the foundation. 14 millimeters of unequal movement might sound alarming for a structure of this unprecedented height, but it did not mean the building was dangerously tilting. Instead, that highly specific number confirmed that downward movement was not perfectly identical across the sprawling footprint, proving that the threat of unequal settlement was a physical reality. It demonstrated that the layered carbonate rock was responding differently depending on the exact load and location above it. The engineers needed to understand and model this exact pattern of settlement rather than simply calculating one average number for the entire site. During the design phase, an interesting analytical comparison emerged regarding how the foundation would actually behave under full load. If an engineering model treated the enormous concrete raft as a perfectly flexible mat, loaded only by pure downward weight, the theoretical differential settlement was significantly larger than what was actually measured on site. This critical discrepancy between the simplified flexible model and the actual physical data revealed a crucial mechanical reality. If the foundation were entirely flexible, the varying ground stiffness would have forced the wings to settle at noticeably different rates, bending the raft out of shape. But the physical measurements proved that the differences in settlement were being tightly restricted and controlled. Something massive sitting above the foundation was actively limiting how differently the three distinct wings could move. The crushing weight of Burj Khalifa was the exact force driving the foundation downward into the ground. But the immense rigidity of the tower itself was also influencing how that downward movement was distributed across the massive concrete raft. The structure above was acting as a stabilizing constraint on the ground below, preventing any one wing from breaking formation. This revelation shifted the entire understanding of how the megastructure maintained its vertical alignment over variable geology. This complex physical relationship is known in engineering as soil-structure interaction. The relationship between a building and its foundation does not move in only one direction. The layered ground beneath the site naturally affects how the foundation performs, offering subterranean resistance that varies slightly from one point to another. But the foundation and the colossal structure rising above it also push back, fundamentally altering how those subterranean layers compress. Imagine placing a heavy weight on a series of independent flexible trays resting on slightly uneven sand. The trays will sink at noticeably different rates, depending on the exact density of the material directly beneath them. Now imagine those same trays securely bolted to a massive rigid steel and concrete frame. When one section attempts to sink slightly faster, the rigid frame above resists the bending motion and forces the load to redistribute evenly across the entire system. This is exactly what the superstructure of Burj Khalifa achieved. The extreme stiffness of the central hexagonal core and the three structural wings effectively tied the entire piled raft foundation together. The tower did not magically save itself from sinking. Instead, the superstructure stiffness actively contributed to the response of the combined foundation system. It prevented isolated sections of the sprawling raft from settling drastically more than others, forcing the three wings to descend in relative unison. However, translating this immense physical reality into a functional computer model required careful calibration. If engineers modeled the entire tower as perfectly rigid, the theoretical system became unrealistically stiff and failed to match the physical measurements. Through careful reassessment, researchers found that applying a reduced representation of the superstructure stiffness in their advanced models produced a much better agreement with the actual measured settlement patterns. This detail demonstrated that even the most sophisticated engineering models must be calibrated carefully to match physical reality. The foundation was undeniably holding Burj Khalifa up and transferring its weight into the earth. But Burj Khalifa was also heavily influencing how its own foundation deformed into the ground. Relying entirely on complex computer predictions for a megastructure of unprecedented scale was simply not an option for the engineering team. Theoretical models can predict how layered carbonate rock might compress, but engineers needed to verify those calculations against absolute physical reality. They needed to watch the foundation move millimeter by millimeter while actively building on top of it. As construction progressed, the engineering team implemented a comprehensive structural health monitoring program to track exactly how the site behaved. This system did not merely track basic elevation changes with standard surveying equipment from a distance. It included precise foundation settlement surveys, intricate strain measurements within the deep concrete piles, and detailed tracking of how the immense load was actively transferring from the sprawling raft into the surrounding ground. Engineers installed advanced sensors to capture real-time data on pile friction, end-bearing resistance, and overall structural alignment. They also rigorously monitored column and wall shortening, carefully tracking how the reinforced concrete itself compressed and deformed under the continuously growing weight. This intense monitoring process functioned as a continuous sequence of high-stakes decisions rather than a passive observation. Every newly completed concrete floor added thousands of tons of fresh gravitational load to the base. Every added load forced the entire piled raft system to respond, pushing slightly deeper into the layered carbonate soils. And every new survey measurement provided immediate feedback on whether the observed physical behavior remained compatible with the strict engineering expectations. As the enormous three-winged frame rose higher into the sky, the measured settlement profile gradually and predictably moved further downward into the earth. The structural monitoring program essentially connected the theoretical engineering design with the raw physical reality of the Dubai construction site. It allowed the engineering team to compare the continuously updating measured curves directly against their original predictive models in real time. They were not building blindly and hoping the ground would hold. They were building while actively measuring the Earth's response. And when they finally compared the observed settlement with their earliest conservative expectations, the apparent danger of downward movement changed direction once again. During the early design phases, engineers had to establish a safe upper limit for how far the massive structure might sink under its unprecedented weight. Based on assumed gravitational loading and the complex physical parameters of the layered subterranean ground, some early conservative models generated a predicted final settlement range. These initial calculations allowed for approximately 70 to 75 millimeters of total downward movement across the foundation system. It is important to understand that this figure was a theoretical design prediction generated to test the extreme limits of the structure. It was not a confirmed physical measurement of how the building was actually behaving. As the structural health monitoring program tracked the physical settlement of the site, the raw data revealed a compelling shift. The measured downward movement during the construction stage was noticeably lower than those original conservative design predictions. Furthermore, when researchers later reassessed the foundation behavior using updated analytical models that incorporated the true stiffness of the concrete superstructure, the new predicted maximum settlement was also lower than some of the earlier baseline calculations. This engineering reality completely changes how we must view the initial settlement data. The correct conclusion is not that the tower never sank into the ground. The correct conclusion is that downward settlement absolutely occurred, but the measured physical behavior during construction remained broadly within, and in important respects better than, the conservative scenarios that engineers had prepared for. The massive piled raft and the highly rigid superstructure were successfully managing the extreme loads together. However, acknowledging this engineering success does not mean we can automatically assume that all long-term downward movement permanently stopped the exact moment construction finished. The most detailed publicly discussed settlement profile originates from an engineering reassessment paper that utilized physical data available up to February 2008. That date was well before the towering structure was fully loaded and officially opened to the world. This timeline leaves us with a final distinction between what the historical engineering records physically prove and what the public can actually verify today. The sprawling foundation of Burj Khalifa remains equipped with an extensive array of highly sophisticated monitoring systems. These embedded sensors were designed to continuously track foundation settlement, structural tilt, dynamic acceleration, and the overall physical response of the tower to environmental forces. But the mere existence of a world-class monitoring network does not mean that all of its raw data or updated measurements are publicly released. The detailed engineering papers covering the foundation reassessment referred to relatively small amounts of additional downward settlement occurring just before the official opening. However, those same public documents do not present a complete, continuously updated foundation settlement history covering every single year of the building's operational service life. Public engineering records absolutely confirm that Burj Khalifa settled into the earth during its construction phase. They also clearly demonstrate that the measured behavior was broadly consistent with strict engineering expectations. But those accessible records do not provide an unbroken public ledger of every millimeter of subterranean movement that has occurred in the years since the ribbon was cut. Without access to long-term post-construction survey data, external engineers cannot definitively analyze how the layered carbonate rock has responded to decades of sustained concentrated pressure. We cannot publicly see the precise long-term effects of cyclic wind loads or microscopic changes in deep groundwater conditions over time. This lack of continuous public data does not prove that Dubai is hiding a structural crisis, nor does it suggest that the tower is facing an imminent collapse. It simply means that the external scientific community and the general public cannot independently verify the exact present-day settlement profile. The unanswered public question is no longer whether the world's tallest building has ever moved downward. The geological and structural evidence definitively proves that it has. The remaining question is whether every heavy section of that immense three-winged foundation has continued to move perfectly together throughout its entire service life. At the beginning of this investigation, the revelation of a downward foundation shift appeared to signal a catastrophic engineering failure. But the reality beneath the surface reveals a much more sophisticated relationship between the architecture and the earth. The layered carbonate ground compressed. The massive piled raft foundation responded. The rigid three-winged tower actively distributed the structural forces, and the entire system settled downward into the earth. Engineers did not build the tallest tower in human history on the naive assumption that it would never move. They carefully measured that physical movement, compared the data against their theoretical predictions, and proved that ultimate stability depended entirely on controlling the differences across the foundation. Burj Khalifa does not remain perfectly vertical because nothing beneath it moves. It remains vertical because engineers designed an interconnected system fully capable of tolerating and managing that movement. The illusion is that the world's tallest building stands on perfectly unmoving ground. The engineering reality is that it was designed to survive movement measured in millimeters. This documentary is produced for educational and analytical purposes, relying on available public engineering records and historical structural data. It does not provide professional engineering advice, and it acknowledges the limitations of publicly accessible long-term monitoring data. Do you think megastructures should be required to publish their ongoing structural health data, or is that a matter of private security? Share your perspective in the comments below, and subscribe for more investigations into the engineering realities hidden inside our modern world.